Hi everyone, welcome to CVPR 2023, and in this paper we are going to talk about structured kernel estimation for photon-limited deconvolution. We aim to restore images on the left with two layers of degradation. First we have motion blur, and then we have short noise due to low illumination. Compared to conventional deblurring algorithms, this problem is much more highly ill-posed. As you can see, conventional blind deconvolution, which uses alternate minimization, doesn't work in this scenario. So in this paper, we provide a new approach for photon-limited deconvolution problems. We use spatially invariant blurs, so we have this nice forward model we can use. We have the clean image, blurred by an unknown kernel, with addition of Poisson short noise. We frame the photon-limited blind deconvolution problem as an optimization problem first. We need to estimate the unknown blur kernel, and hence we can correspondingly estimate the clean image as well. Here is the iterative scheme we use. We have a non-blind pre-trained solver, which has input the blur kernel and the noisy blurred image. Using a kernel estimate at a fixed iteration and the noisy blurred image, we calculate the reblurring loss. Once we have the reblurring loss, we can calculate its gradient with respect to the kernel and perform gradient descent on the kernel. We repeat this process until convergence, until we have a kernel estimate. Plugging this kernel estimate into the non-blind solver also gives us the clean image. As you can see, this approach doesn't really work very well. We have the restored image in the middle, and there is a lot of residual blur still left in the image. The reason for this residual blur is that the search space in which we find the kernel is just too big. We're searching for the kernel in pixel basis in which most of the entries are non-zero. So our diagnosis for this problem is we need to search for the kernel in a differentiable and lower dimensional search space. Here's how we do it. We imagine the blur kernel in terms of the camera trajectory. The camera trajectory itself can be viewed in terms of these three key points. Given these key points, you can generate the camera trajectory using spline interpolation, and hence you have one-to-one mapping between these few key points and the blur kernel. We can convert this one-to-one mapping into a differentiable form using a neural network. We learn a network called Kernel Trajectory Network, KTN, and train it using synthetically generated data points, and train it using MSE loss. Once this network is trained, we can use it in the iterative scheme described a few minutes ago. You can see this iterative scheme isn't really different, except the fact that we are using KTN to represent the kernel. We are not searching the kernel in the pixel basis anymore, but we are using this vectorized key points representation. As you can see, this leads to really improved deconvolution results. There is no residual blur in the image, and the resulting image is so much more cleaner. To conclude, we start with an iterative kernel estimation scheme for blind deconvolution problem. This scheme converts the conventional image and kernel optimization to a kernel optimization scheme only. Next, to improve the deconvolution results, we imagine the blur kernel in a smaller key points representation. Plugging this representation into the iterative scheme leads to much better deconvolution results. For further details on our paper, you can refer to Structured Kernel Estimation for Photon-Limited Deconvolution, now available on arXiv. Thank you for your time.